For this example, we have cos theta is equal to negative 0,5. And the question asks, what is the value of theta in the interval of 0 to 360? So the same as the previous question. Here's the graph of the situation. So that's the graph of cos theta. And here's a line for cos theta is equal to negative 0,5. Here we have the 4 points where it intersects with the graph. We're in the range of theta values displayed in the graph. The line would cut it at 4 different points, but since we want to know the values in the range of 0 to 360, we'll only look at the positive half of the graph, where in that case you have two solutions that will answer the question. And since we have the graph in front of us, we sort of have the cheat code of what the value should be, but you normally wouldn't have this. So at least we can use it as a reference point to confirm that our answers are correct at the end. Anyway, so we'll know we need to get 120 and 240. The next, we just need to apply the same 4 steps as we did for the previous example, starting with determination of the reference angle. So determining the reference angle would be pretty simple to do. You just take the cos to the other side and find cos inverse of 0,5. And notice something important. I changed it from negative 0,5 to 0,5. And that's an important step for this method. If you have a negative value on the right side, you must change it to a positive value before you take the inverse. But don't forget that the original value is negative, and we'll need to use that fact in the next step. But anyway, when you find cos inverse of 0,5, you get the reference angle as 60 degrees. Then for step 2, you need to note the sign of the function value. And the question was cos theta is equal to negative 0,5. Therefore, the sign of the function value is negative. Then for step 3, you check in which quadrants the function has the sign from step 2 using the abbreviation ASTC, which as a reminder stands for All Students Take Calculus, and represents which functions are positive in each of the 4 quadrants. So since we have a negative value this time, we have to see in which quadrants cos would be negative. Therefore, any quadrants here that are not labeled using C or A, since A is all, are the quadrants we're thinking about. So normally cos would be positive in the first quadrant and the fourth quadrant. But since we want the negative value, it means we need to look at the second and the third quadrant. Therefore, cos is negative in the second and third quadrants. Then for step 4, we need to determine the other angles besides the reference angle by learning and applying quadrant rules. So these are the quadrant rules, and you'll need to know these by head going forward because in the exam you won't be given the quadrant diagram. So anyway, we noted that cos is negative in the second and third quadrants, and the reference angle is 60 degrees. So for the second quadrant value, we would say 180 minus 60 degrees, giving a value of 120 degrees. And for the third quadrant, the rule is 180 plus 60 degrees, meaning 240 degrees. And that's the solution. And we know these are correct because we noted before from the diagram that 120 and 240 degrees would be the two solutions. Therefore, the values of theta that will satisfy the equation in the question are 120 and 240 degrees. And there's a key thing to note here. Notice that in the actual solution, this time we didn't actually include the reference angle of 60 degrees. And that's because it isn't a solution in this case. And this example more so shows why it's actually called a reference angle, in that you refer to it in finding your solution, but it isn't necessarily a solution itself. So in the previous example, we had the 30-degree reference angle was only part of the solution because the first quadrant was part of the solution, because that's where sine theta is positive. But in this second example, we had cos theta being a negative value, so the first quadrant wasn't included and therefore didn't form a part of the solution. Therefore, the reference angle of 60 degrees also wasn't a solution. Now I'll do a few more examples, but I'll answer the following few questions assuming the student is comfortable with all the material we've just revised, meaning you're familiar with all the different identities such as the quotient and the square identity, and you understand how to work with the quadrants. That being said, here's an example. So this is a different sort of example. Here we're given an equation with a bunch of different trig functions and angles already, and then we need to evaluate the whole thing without using a calculator. So this is the sort of question where you need to use the knowledge you have regarding the special angle triangles. And then you'd also apply some of the identities, such as the ones for the negative angles. And then this time, there's also another new thing, which is you have an angle greater than 360 in the equation. So how would you deal with that? So I'd suggest pause and give it a try first by yourself, then I'll give you the full solution. Here's the solution. So here's the equation we had in the question. Then the very first step with these sort of questions is try break down the numbers to something more familiar. And the best example of that would be the different rules that apply to the different quadrants. So we know that in the first quadrant is just theta as it is. Second quadrant is 180 minus theta. Third quadrant is 180 plus theta. And fourth quadrant is 360 minus theta. So if it's a number greater than 180, then try relate it to 180 somehow. If it's a number less than 180, see if it's between 180 and 90, and if so, then try to rewrite it in terms of 180 minus something. So in this example, we have sine 225. Since it's more than 180, we can make it as the third quadrant version, which would be 180 plus 45. Then this cos negative 45 term, you would convert it using the rules for negative angles. And for cos, we saw that cos negative theta is just the same as cos of theta. So this becomes cos 45. Then for this cos 420, where you now have a number bigger than 360, in those cases, the first thing you do is represent it as 360 plus some number. In this case, that would be 60. And the reason for this is related to the whole aspect of periodicity, because since we know the graph of this function would essentially keep repeating over and over, we know that any value greater than 360 is just a repetition of whatever value the function had for a theta value of 360 degrees less. So applying that to this value gives you 360 plus 60. And then since we know the value just repeats every 360 degrees, cos 360 plus 60 is essentially the same as saying cos 60. Therefore, you can then rewrite it as cos 60 in this third step. And then for this denominator value, we had it being less than 360, but reasonably more than 180. So that's why we didn't write it as 180 plus 100 and something, because it was closer to 360. So generally, when you have an angle between 180 and 360 degrees, such as this 315 degree value, you'd rewrite it in terms of 180 or 360, depending on which of the values it's closer to. So how you would know which one is closer to is by seeing whether the number is above or below the halfway point. The halfway point between 180 and 360 is 270 degrees. So if the number is less than 270 degrees, then you rewrite it in terms of 180. And if the number is greater than 270 degrees, it means it's closer to 360, and you should rewrite it in terms of 360 degrees. So since 315 is greater than 270, that's what we did in this case. And I rewrote it in terms of 360 degrees. So that's all the breakdowns in the second step. Then in the third step, so we know we have this angle as sine 180 plus 45. Then you would think, which quadrant does this rule apply to? So the 180 plus theta rule applies to the third quadrant. Then you would say, what sign does that function have in that quadrant? And then from ASTC, we know that in the third quadrant, the sine function would have a negative value and would be the same as negative sine of theta. Therefore, sine 180 plus 45 is the same as saying minus sine 45. Then cos 45, it just stays the same. You don't need to change it yet. And cos 360 plus 60 is cos 60 as previously mentioned. And then for the tan 360 minus 45, you notice that this is the rule for the fourth quadrant. And in the fourth quadrant from ASTC, we know tan is negative. So it'll have the same value as negative tan of whatever angle is being subtracted from 360, which in this case is 45. Therefore, it's the same as minus tan 45. So we've broken down the angles and functions as much as we could at this point. And the only thing left to do now is substituting each of these with the values they should have based on the special angle triangles, which you should know by head. I mean, you don't necessarily need to know exactly how it looks by head, you just need to know how to build the triangle. Then you just say sine 45 is equal to 1 over root 2. So that's the value for sine 45, and then cos 45 has the same value as well, so it's also 1 over root 2. Then you'd remember from the 60 and 30 degree special angle triangle that you had the cos of 60 degrees be the adjacent, which is 1, over the hypotenuse, which is 2, giving a value of half. So that would be minus half. And from the 45 degree angle triangle, you know that tan 45 is just 1. So you can just substitute the value in there. Then these two terms multiply by each other to give a value of half, with the minus sign outside, don't forget that. And this is just negative 0.5. And denominator stays as is, and it all comes down to a value of 1. And that's the final solution to this equation. Another thing worth noting about the situations where you have an angle greater than 360 is first subtract 360 from the angle. And luckily this time it was pretty small, so you just ended up with 60 and you could take it as is. But what if you had been given something like an angle of 1000 degrees? That's entirely possible. And in that situation, even after subtracting 360, you'd still have a pretty big number of 640. And in those situations where you still have a number greater than 360, you keep repeatedly subtracting 360 until you have a value that's smaller than 360. So if you had 1000, you'd say 1000 minus 360, you get 640. Then you'd say, okay, this is still greater than 360 degrees. So you subtract 360 again, and I think that would give you 280. And then now you'd be like, oh, okay, so now it's smaller than 360. Then you'd see, okay, yeah, now I can relate it to a quadrant, and then continue as per usual. And then another thing is, once you do finally end up with your solution, the great thing is, since you have a calculator, you can always verify it by just typing in this whole equation into your calculator and see if you get the same value that you did from working it out by hand. And if you did, then great, then there's no problem. Let's look at another example. If sine 49 is equal to c, express the following in terms of c. First part says sine 131. First thing to do with these sort of questions is related to the quadrant rules, so that you can rewrite it in terms of something simpler. So here we can tell that 131 is pretty close to 180, so rewrite this in terms of 180. So 131 is just 180 minus 49. And the 180 minus rule is for the second quadrant. And from ASTC, we know that in the second quadrant, sine is positive. Therefore, this would just be equal to sine of 49, which is just the same as c. Then for part B, we have cos negative 41 degrees. And whenever you see a trig function with a negative number in it, first try to rewrite it using the rules for negative angles. And for cos, we know that cos of negative theta is just cos theta. So cos negative 41 would just be the same as cos 41. And then now the problem is, while we've simplified it to a pretty good degree, we can't yet see how it relates to sine of 49, because we need to relate this to it so we can write it in terms of c. So one way we could bring a 49 in this is by saying 90 minus 49, which is the same as 41. Then this rule of subtracting an angle from 90 isn't something we're familiar with from the quadrant rules we've already covered, because those are only in terms of just theta, 180, or 360. But somewhere where you should be familiar with this from earlier was where I mentioned that cos and sine are cofunctions, where cofunctions have the same value when their angles are complementary, meaning when they add up to 90. Therefore, cos of 90 minus 49 would be the same as sine of 49, which again is exactly the same as C. Then for part C we have cos of 311 degrees. We can relate this to the quadrant rule for the fourth quadrant, which would be 360 minus 49. And from ASTC we know that in the fourth quadrant, cos is positive. Therefore, cos 360 minus 49 is exactly the same as cos 49. And the question asks us to relate it to C, which is sine 49. So how do you rewrite this in terms of sine 49? I'll admit that this one is a little bit trickier, and only by seeing the trick done once before will you be able to know about it. And the trick this time is you rewrite cos 49 as square root of cos squared 49. And this is useful because using the square identity of sine squared theta plus cos squared theta equals to 1, we can rewrite this in terms of sine 49 as square root of 1 minus sine squared 49. And since we know that sine 49 is C, we can rewrite this as square root of 1 minus C squared. And that's the solution. And for part D, we have tan 229 degrees times cos of 229 degrees. And by the way, this dot in between just means multiplied. It just used to show that tan 229 and cos 229 are separate functions. But anyway, the trick this time is to apply the quotient identity and rewrite tan 229 in terms of sine and cos 229. Then these two cos 229s conveniently cancel out, leaving just sine 229. And 229, we can relate it to the quadrant rule for the third quadrant, which is 180 plus theta, which in this case would be 180 plus 49. And from ASTC, we can tell that in the third quadrant, sine is negative. So this would be equal to negative sine 49, which is just negative C. And that was the final part of the question. And something that I think is worth clearing up right now and just clarifying for you in case you may be a bit iffy about it is the whole usage of indices with these trig functions, such as we saw in this part, where you had the cos squared and sine squared functions. And this is that sine squared theta is the same as saying sine theta in brackets, the whole thing squared, and is not the same as saying sine of the angle theta squared. Another way to understand this is using sine cubed theta, where sine theta in brackets cubed would be written as sine cubed theta. I think a useful way of thinking of it is as if the sine theta is x. So the sine cubed theta is just the same as saying x cubed. I hope that clears it up. Then I'll go through just two more examples before I wrap up the fundamentals revision section. Simplify the following equation to a single term. For part A we have 1 over cos squared A minus tan squared A. The goal is we need to simplify this as much as possible into a single term instead of the two terms we have here. So the easiest way would be by combining them as fractions with the same denominator. So since this has cos squared A in it, we can just rewrite the tan squared A as sine squared A over cos squared A, giving 1 over cos squared A minus sine squared A over cos squared A. And since these have the same denominator, you can combine them easily, giving 1 minus sine squared A over cos squared A. And from the square identity, 1 minus sine squared A is just the same as saying cos squared A. Since the numerator and denominator are the same, this just simplifies down to 1. Then for part B, we need to simplify 1 minus cos squared alpha over cos squared alpha minus tan squared alpha. Can apply a similar trick as the previous part by changing the tan squared alpha to sin squared alpha over cos squared alpha. Then combine these two into a single fraction, giving 1 minus cos squared alpha minus sin squared alpha all over cos squared alpha. Then we can group the cos squared alpha and sin squared alpha terms into a single bracket by putting the negative outside, giving 1 minus cos squared alpha plus sin squared alpha, brackets closed, over cos squared alpha. From the square identity, you know that cos squared alpha plus sin squared alpha is just 1. Finally, just giving 1 minus 1 over cos squared alpha, making the final answer just 0. And we can now look at the final example, but before that, I'll just make a bit of a modification to the 4-quadrant diagram. Now that you're used to and familiar with the previous one, I think it's worth adding a few terms related to 90 degrees. I didn't change it that much. Basically, the only addition is the cofunction rules. So the cofunction rules only apply to the first and second quadrants, which can both be written in terms of 90 minus an acute angle or 90 plus an acute angle. But it's worth keeping in mind that I put these in different color because the ASTC rules don't apply to them. So just keep that in mind. The first addition is to the first quadrant, where it's the basic cofunction idea, where we know that sine 90 minus theta is cos theta and cos 90 minus theta is equal to sine theta. Then angles between 90 and 180 can be written in terms of 90 plus theta. And from mathematicians looking at the graphs of cos and sine theta, they were able to tell that sine of 90 plus theta is equal to cos theta. So it's the same result as sine 90 minus theta. And then a sort of a new thing or something different that you need to keep in mind is that cos 90 plus theta is equal to minus sine theta. So it's not the same as cos 90 minus theta where it's just sine theta. This time there's a minus in front of it. So if you already understand the quadrant diagram pretty well in terms of these quadrant rules and without these 90-degree angles, this addition is pretty basic, and I think an easy way to remember it is just that in the first quadrant you have the basic cofunction rules, and then in the second quadrant, this time the only difference is it's 90 plus theta, and they have the same outcomes as the first quadrant cofunction rules, except that the cos 90 plus theta is equal to negative sine theta and not just sine theta. So all in all, if you're still a bit iffy with the 4 quadrants, here's the easiest way to keep it all in mind. So first keep in mind that you have 4 portions to it, separated by these 2 lines, and then know that it starts in the top right going anti-clockwise and ends at the bottom right. And each portion of it represents a range of 90 degrees, where the first one is 0 to 90, second 90 to 180, third 180 to 270, and fourth 270 to 360. So that's the first thing to keep in mind. Then second thing to keep in mind is the quadrant rules for all 4 quadrants. So you just have to keep in mind that first quadrant is just theta, second quadrant is 180 minus theta, third quadrant is 180 plus theta, and fourth quadrant is 360 minus theta. Cool. Then the next thing to keep in mind is this abbreviation ASTC, which you can remember from the phrase all students take calculus. And what the abbreviation indicates is which trig function has a positive value in each quadrant, where in the first quadrant all of them have a positive value. In the second quadrant, since it's S, it means the sine function has a positive value. In the third quadrant, since it's T, it means the tan function has a positive value. In the fourth quadrant, since it's C, it means the cos function has a positive value. And all other functions are negative. So that's how you remember the basic 4 quadrants. Then to add on the 90-degree rules, in the first quadrant you just know that it's the two basic cofunction rules, where the angles used for the sine and cos function should both add up to 90. So one would be 90 minus theta and the other is theta. And then for the second quadrant, just keep in mind that it's almost exactly the same, except this time it's 90 plus theta, since the angle needs to be greater than 90. And the sine function is equal to cos theta in the exact same way as it is in the first quadrant, but the cos function on the other hand is negative sine theta, unlike in the first quadrant. And once you keep those 4 or 5 facts in mind and just try to apply them from your head for a few different questions, you'll get used to it pretty quickly and you'll automatically know what the 4 quadrants are and how you need to use them in different questions. Now that that's out of the way, let's look at a final example under the fundamentals section. The question says you need to simplify the following equation: tan squared b times cos squared 90 minus a plus sine squared 90 plus a times tan squared of b. So there's two unique things about this example. One is now we have trig functions with 90-degree values inside the brackets. And the other thing is that now we have two different sort of angles, where now we have an angle of A as well as an angle of B. Whereas in the previous examples, it was always just the same angle of theta or alpha or whatever. But this time there's two of them. But there's no stress, we'll just break it down one step at a time. So the first obvious thing to do is change them to the forms that they have using the cofunction quadrant rules. The first is that cos 90 minus A is just the same as sine A. Then the second is that sine 90 plus A, which would be in the second quadrant, has the same result as sine cofunction rule from the first quadrant, which was that sine 90 minus A is cos A, meaning that sine 90 plus A is also cos A. Then you sub these in, giving tan squared B times sine squared A plus cos squared A times tan squared B. Then notice that both terms have a tan squared b in them, so you can factorize it out, giving tan squared b times sine squared a plus cos squared a. And from the square identity, we know this would just be equal to 1, leaving the final answer as just tan squared b. So it seems like the whole different angle thing of a and b didn't really end up being such an issue in the end. And that concludes the fundamental section, and we can now move on to some new trigonometry material. And the first of this is compound angles.